Hello, everybody. We're getting this started soon. Okay, so at the end of this entire stream, everything will be saved, so you can go back and watch everything at the end. But we're going to be going through everything now, and I'm going to start with number one and pretty much be going all the way through. If you have a question that you would really like to see done, please wait till we're done with the current question. Like if I'm doing number one, you can request number four, and we'll take a look at that after I'm done. But just make sure you guys are, keeping up with the chat. Let me know anything that doesn't make sense. That way I can explain it. So number one. It says the charge plus Q is uniformly distributed throughout a solid insulating sphere. Okay, bye, Mom. A charge Q is uniformly distributed on a solid insulating sphere of radius A. Let me get a darker marker. That's better. And there's a hollow sphere around it with radius B, radius C. And they want to know the outer shell. Okay, so they tell you that this shell has positive charge Q. And note, it says it's an insulating sphere, so I'm going to label it rho. Everybody knows why. Then here, this is going to be a net charge of negative 3Q. Or not a net charge, I'm sorry. A charge of negative 3Q. Yes, so the outer has negative 3Q. And this has Q, but we don't know what this has. So we'll have to figure that out. First things first, if this has charge plus Q, then by induction, this inner surface should have negative Q, right? So if the outer surface has negative 3Q and the inner surface has negative Q, then the Q net must be negative 3 plus negative Q, negative 4Q. And now we're going to find the radius at r less than a. Okay. Also, if somebody who's currently watching the stream can go on the Google groups and make a post, because I totally forgot, and just say, follow Matt, on YouTube, Physics with Matt, and that way we can get more people coming in the stream. Probably only you guys from SI know about today. Totally forgot to post it on there. So if somebody can go on groups.google.com and go make an announcement or a post and just say, hey everybody, Matt is hosting a live stream, check it out, and put my YouTube name and all that. Cool. Okay, r less than a. Oops. Okay, I'll put that over there. The Q net on the outer shell is equal to negative 4Q. And that's because this is negative 3Q, this is negative Q by induction, so the total is negative 4. Now, r less than a, not dA. It's already going to be a sphere, so we're going to use what? 4 pi r squared. Remember, when you're doing Gauss's law, to draw your Gaussian surface. This is R1, R2, R3. And finally, R4. So, according to my diagram, I'll label this as R1. I've already done the integration. Pretty much the step before this is E dot dA. You have to check to make sure that the electric field vector is parallel or anti-parallel to the E vector, and then you're good to go. Otherwise, EA cosine 90 would be 0, right? Okay, now the right side, which is Qn over epsilon sub naught. And what is this Qn? That's going to be the charge enclosed within this sphere. Now we're told that it's an insulating sphere and it's also uniform. So we can use ratios. So I'm going to say rho is, let me do this with another color. Rho is Q over the volume, which the total volume would be what? 4/3 pi. And this is going to be A cubed, right? And then if we're talking about some smaller portion of that charge, smaller radius, and I'll say R1 because that's what I labeled it. Okay, so now what do you do with this? You're pretty much saying that I have a small sphere. All right, this is my total sphere. This is my small sphere. It should have the same charge density, right? That's what it means for charge density to be uniform. Okay, so now you're gonna want to solve for Qn, right? So now Qn multiply this over is gonna be 4/3 pi Q R1 cubed over 4/3 pi and A cubed. All this will cancel. Oops. That's my birthday cards. So all this will cancel, and you're left with and this is saying that the charge Qn is a ratio of Q in proportionality to R1 cubed over A cubed. Pretty much saying A cubed is the total volume, R1 is the small volume, so therefore smaller charge, right? Okay. So now you're going to take this and plug it in here. Let's go black and back to blue. And always make sure, guys, that you finish the integration on this side of Gauss's law before you start on the other side. So I'm going to plug in this Q in right here. Q R1 Q over A Q epsilon naught. And now finally, electric field is just going to be what? 1/4 pi epsilon naught. I can substitute it as K if I wanted to, but get in the habit of leaving epsilon naught in your equations. We're just going to be using it a lot more as we go along in the class. So 4 pi, this R1 squared will cancel out with this R1 cubed. So we're going to get Q R1, right? Because you get two of these cancel out with two of those. And then divided by 4 pi epsilon naught A cubed. Now, how do you know you're right? So that's Coulomb, that's meter, and then this is Coulomb squared over Newton meter squared, right? And then that's meter cubed. Coulomb squared over Newton meter squared. So let's go ahead and do all that. This one divided by that will cancel out one. You'll have a Newton meter squared on the top, right? This will flip up, or you can see it this way. Two of those cancel out with two of these. And then you have meter over meter, which will cancel. So this Newton This 2 is canceled. This Newton will flip up, and you'll get newtons per coulomb. You can do that every time to make sure you're like 100% right. And that's part A. So everybody make sure you're good with this because I only have limited whiteboard space. So we'll be doing lots of erasing today. Lots of erasing. And also if you're wondering what this is, I've had it up for like a long time, but it just means change is good, or every little change is good. It's in Japanese. I don't know. I like anime. But anyways, that's a good living thing to live by. You know, if you make a little progress with E&M each day, you're good. Don't get so down about E&M. It's difficult, but it'll be over. And then when it's all over, you can say, isn't it? Just like Dr. Brenda. There you go. Okay. Now I think we're good with this. So I'm going to go ahead and erase most of this. And what I'll do, just so we're consistent, I'll keep A up here and then I'll write the answer, okay? Okay. No, that's right. Okay, part B of this says we're A less than R less than B. So now, where are we? We're right here, right? So this is simpler because now we have the total charge distributed over here, and it's just going to be, it's going to be the same dA, but except a different radius, right? I'm talking about R2 here. R2 squared. And then this is going to be what? Qn is rho V. So, and the volume is going to be where the charge is actually present. So the real key part for the right side here is this is Qn. That's talking about the actual charge enclosed. So that volume must actually be where the charge is present. It's not going to be R2, it's going to be A, right? Okay. So now go ahead and write that. Rho and 4/3 pi A cubed, right? And then now, last step, it's going to be rho, the 4 pi will cancel, and you'll have A cubed over 3 epsilon naught, right? I forgot the epsilon. Okay, so that one's not too bad. Oh, I missed something. The R2, right? R2 squared. There you go. Again, dimensional analysis to check yourself before you wreck yourself. So rho is coulomb per meters cubed. A is meters cubed, so already there we have some cancellation. 3 R2, that's meters squared. And this is what? Coulomb squared per Newton meters squared. Cancel. Oh. Cancel there. And then this coulomb will cancel out with one of these coulombs. So you have coulomb on the bottom, Newton there, and it's newtons per coulomb. Awesome. So do that every time. You won't be wrong unless you're wrong, but it's okay. We'll get to how to do that. You can also use limit approximations to figure out, as for this one, let me see. As R approaches the value of A, so as R approaches A, you could take the limit of that, and it should give you the same dimensional analysis. But this is an easier way of doing it. Again, I'm going to go ahead and erase all this that we did. I'll write the answer. And C has this right here, which is B less than R less than C. Okay, so nobody has entered in the chat yet. Everybody's just watching. I want this answer. Someone please type it in. This is an insulator. That's a conductor. So if I'm inside the conductor, what's the electric field? Oh, why can't we just call Qn plus Q if it's given as the charge of the insulating sphere? Oh, you could. That's true. I kind of solve it in a way where I will always have rho as my answer. So yes, if you plugged in rho for what it would be, right? What's rho? Rho is Q over V. If you plug this rho into here, you should find that same answer as if you just plugged in Q. However, sometimes you're just given rho. So this is kind of always my go-to way of solving it. I'll always leave rho, sigma, and lambda in my answer because that's usually what's given. You know, you're usually given like a picture and you're given that. Sometimes you're given Q. When you are, consider yourself lucky. Right? Yeah. So, okay, there's that. And then, as everybody said now, that's 0 because we're inside the conductor. And then lastly, we're outside the conductor. So here's the easy way to think about this. For D, R greater than C. Qn is what we already wrote it as, right? Which could be, like Garrett said, this Q. And then plus, it's going to be the charge distributed along the conductor, which let me look back at the problem. Blah, blah, blah. Okay. So earlier we figured out that the outer shell has a net charge of -4Q. So that's going to be the total charge on that outer sphere. Let's just say we were given Q's. This is how it'll be easier. I have a positive Q, and I would add, or I'm going to add a negative, not 3, a -4 Q. That's this charge due to the insulating sphere and this charge due to the conducting hollow sphere. That would be the easy way if you're given Q. However, usually you're not given Q, so this can become a little more involved. So this Q is distributed along the volume, so it's going to be rho times V, right? Rho times V. Then what about this one? The -4 will stay because that's just an amount, that's a constant. But what is that Q? It's distributed over a sigma. So I'm going to write -4 times sigma A. And what area am I talking about? What area? The area I'm talking about is always going to be this outer shell. Why? Because it's a conductor, and where do charges lie on a conductor? On the surface. So the area that you're trying to talk about will be this area of the conductor. So the outer spherical shell uses a sphere. So you're going to write that. Now we already did this one, right? We already went through that on this part. So you can just plug in 4/3 pi a cubed, 4/3 pi a cubed. But let's look at how to do this one. So sigma times A. Let's just say you're given sigma, so you can have it in your answer. But you need to find out what that A is, right? So it's just going to be the area of a sphere. That's it. So you have the volume of a sphere, which is 4/3 pi And for this sphere, it'll be, isn't this sphere hollow? It is hollow, right? So this is what the volume will look like. C cubed minus B. Let me erase that. Like this. That's the outer shell minus the inner shell, right? But what about the area? The area is just going to be the outer surface. So you will simply define it as that, which is just the area of the sphere, which isn't too bad, right? 4 pi, and not B, because B is the inner, I'm going to use C squared. Why is it not C squared minus B squared? Well, the simple thing is, where is the charge located? The charge is located on the outside of the conducting sphere. So I have to use the area that is where those charges are. So if the charges are on the inside, I would use 4 pi b squared, but they're not on the inside, they're on the outside. So 4 pi c squared. So I'm going to use this area with my sigma and plug it all in. We said earlier this was 4/3 pi a cubed, because this is this one minus 4 sigma, and this area that I wrote here. So there you go. This is literally your total Qn. And don't forget epsilon naught. So now I have to write the whole thing. Again, what is this? This is going to be the area of the Gaussian surface. Because that's R4. That's where I'm at. It's going to be equal to this whole entire thing. So I'll go ahead and write it out. And I may not forget, this is all, divided by epsilon naught. Right at the bottom there, there's epsilon naught. Okay, I'm going to have to erase a little. And now let me do the rest. So this 4 pi will cancel out with this 4 pi and this 4 pi. So there's that. And this R4 squared will just stay on the bottom. So let's go ahead and write it. I have rho, the pi cancels into 4. I have a cubed. And I can say like this, R4 squared. There's a 3 there, and there's an epsilon naught. You can go ahead and combine the fractions if you want to, but I'm just kind of doing the math. You can clean it up. And then minus, there will still be a 4 here. Sigma pi cancels c squared over R4 squared epsilon naught. So everybody make sure my math is good here. I'm pretty sure it is. Divide this 4 pi, that one goes out, that one goes out. This becomes 4, that pi goes out. So you combine those two if you want. I'm not going to get into the nitty gritty of that. But that's just algebra from that point. Okay, and the last part of the problem. What charges appear on the inner and outer surfaces of the shell? I kind of already did this. Notice how the way I did the problem, I already solved that portion of the problem before I even got there. That's because I'm trying to figure out if this one has a charge Q, what by induction, what must happen to the inner surface, right? So you have to always kind of think like that, like, oh, there's a charge. A conductor must have an electric field of 0 inside. So therefore, what must the inner surface have a charge of? Oh, negative Q, right? So for E, the charge on the inner is equal to negative Q, and the charge on the outer is negative 3Q, and the Q net is negative 4. Or am I wrong? Here is going to be negative 4Q on the conductor, right? Negative Q plus negative 3Q. But now we have that positive charge Q. So the actual Q net of the entire thing is going to be 3Q, negative 3Q. Why? Because I'm adding in the smaller one that's Q. And then the net on this is negative 4Q. So negative 4Q plus Q, negative 3Q. So there you go. There's the first problem. Everybody actually did good with this. This is like standard Gauss's law. And once everybody's cool, we'll move on to the next one. Okay, so like I said, when I started the stream, I will just be going straight through down these. However, if you want to see a different one right away, we can do that. How do we get negative 4Q for the Q net? So for this this is an insulating sphere, and it has charge Q. By induction, the rules of induction, this inner surface of the conducting sphere, conductor, must have charge negative Q. Must have. And so on the actual paper itself, it gives us negative 3Q for the outer. So we were given that part. So all I did was the Q net of the outer cylinder, or the outer sphere, I'm sorry. The Q net of the outer sphere is going to be negative 4Q because I'm adding the inner surface area and the outer surface area charge. This charge is negative Q, that charge is negative 3Q, add them together, negative 4Q. Now, I have to take the charge on the conducting sphere and add it to the charge on the insulating sphere. So Q inner is right here, Q outer is negative 3Q. The Q net, let me show it to you guys. Q net is going to be equal to the Q of the insulator plus the Q on the conductor. And let me relabel this. This is Q net of the conductor, right? Yes, that's correct. How's it going? So yes, negative 4 is of the conductor, and then once you add that insulator, you add these two. The insulator is Q, the conductor is negative 4Q, so then you get negative 3Q. So there's that. Okay, any other questions on this? Pretty good, solid problem. You can't get something like this where it's just straight Gauss's law. I'd say go at it right away. Okay. Okay, I'm hoping everybody's good with this. I'm gonna go ahead and erase it. Like I said, after the stream is over, everything will be saved anyways on the YouTube channel, so you can just go back and watch it again. Yep, here we go. And if you want an awesome whiteboard like I have, you can get them for $10 at Home Depot. Put up like little wall hooks, and it's awesome. $10. It's 2 by 4 feet. Okay, we're gonna do number. Okay. Okay, so here they give us Q is 1.0 times 10 to the negative eighth Coulomb, or you can write 0.1 nano Coulomb. 0.1 nano. Now, and we're also given the distance d. Let's go right here. D is 0.2 meters. Now they want to know, what is the electric field and magnitude and direction at the center of the square? So this is easy because it's square. So you can assume theta would be 45 degrees. All these are perfectly 45 degrees. Or rad 2 over 2. And then want to know what's the electric field. Okay, pretty straightforward, guys. So now let's just go around. Due to this charge, there's an electric field this way, right? Due to this charge, there's an electric field that way. Due to this charge, electric field this way. Due to this charge, electric field this way. Okay, and let me label them. This will be 1, this will be 2, this will be 3, this will be 4. So this will be E1, this will be E2, right? E1, oh, sorry, wrong one. This is E2. This is going to be E3, and this will be E4. Okay, so this is great because we have components for every vector. So lots of vectors. But it'll be easy because we know theta. So it shouldn't be too hard, right? So my suggestion to all of you would be, if this is too messy for you, go on to the next page and draw all your vectors again. For me, if I was in the exam, I would just draw all my components on top of my diagram. There's 2 in this direction, I'll call it. There's 2 in every direction. Let me just draw it over here so it's easier. Okay. So this is 1x and E2x. This is E2y and E3y. This is E3x and E4x. And then this is E1y and E4y. The electric fields in the x direction is just going to be E1x plus E2x minus E3x minus E4x. And then sum of the electric fields in the y direction will be E3y plus E2y minus E1y minus E4y. you can do a lot of awesome factoring with this problem because literally every single theta is 45 degrees. So rad 2 over 2, like literally everywhere. And the same distance, right? Right? This should be the same distance. If this is D, this is D. So then draw your triangle. Let's look at like maybe this triangle right here. Now you have what? D by 2. D by 2. And I can assume D by 2 because it's a square. That's the only reason why. This is theta. This is also theta. And then what is that going to be? It'll just be 2d squared by 4, right? Right, everybody? 2d squared by 4. D squared over 4 plus d squared over 4 will be d squared by half. And then take the square root of that. So you get d over radical 2 or radical 2 over 2 times d. That makes sense with everybody. So this here is radical 2 over 2 times d. This is d by 2, that's d by 2, so radical 2 over 2 times d. You could also plug in d if you wanted to, if that made it easier for you. However, I like to work all with terms. It makes it a little bit more clear. So I don't, lose any sig figs. So there you go. This is the distance from every point to the center. This rad 2 over 2 times d. So literally every charge here has the same distance to the center, has the same cosine or sine. So this is going to be really easy. It's going to be really easy. The only thing that will be different is make sure that when you plug in these electric fields, you're looking at, oh, this one is negative 2q, this one is positive 2q, so that way, it's not going to all cancel, right? This kind of looks like it's all going to cancel, but know that these two are stronger magnitudes, so you won't have any actual total cancellation. Okay, here's my eraser. I'll leave the triangle up. So let's look at EX first. What's it going to be? So they all have some of the X direction. They all have K. And they all have, what else in common? What else do they have in common? Do they all have cosine and sine common? Yes. So I'll factor out hold on, I'll just write it just in case anybody doesn't remember. Sine of theta for this theta of 45 degrees is rad 2 over 2. And cosine of 45 degrees is also rad 2 over 2. So we're pretty much going to pull rad 2 over 2 out. And then what else do they share? Rad 2 over 2 times d. And remember, what is electric field? It's QQ over R squared, right? So this R is squared. Okay, and now we can simply, the only thing that we're going to be putting in this bracket is Q. So now let's go down our list to make sure we get all the right values. So E1x, E1 is this one, pointing this way, has magnitude Q. So I'm going to write Q. Okay, now I'm going to add 2x, E2x, and E2 is due to this one, right? Due to this one. And it has a negative 2q. Next, what am I going to do? And then you're going to say, Matt, I thought you were adding it. Why is it negative? Well, because that's negative, right? So I should probably have put this. Am I right? Yes. Yes, of course I'm right. Yes. Why? Because do you guys remember when you're doing electric field or Coulomb's law to use this? Yes, absolute value. Okay. Why? Because you're already picking the vectors. So if I already picked my vectors, I know E1x and E2x is in the positive x hat direction. So I'm going to make sure they're adding, right? Okay. Next, E3x is due to this one, right? Oh wait, E3 is right here, so it's back. There it is. And that has is it going to be minus? Oh. And then for this one, it'll be Q. Oh, that's funny. Does everybody think that the electric field is zero at the center? Does it look like it? Let me look at this property. Okay, so if you guys all remember the, yeah, you guys got zero? Okay, good. Yes. So you can kind of relate this problem to the ring problem. Remember at the center of the ring, the electric field was zero. And that was because you could use symmetry and say that every little point on the ring contributes some electric field in the opposite direction. So it made the electric field at the inside zero, at the direct center zero. So that's actually what's happening here. And I went through a very long process to show you guys and make sure that you don't make the mistake of thinking that there is an electric field, like a value for it here. It is zero, and you can prove it by looking at that. That cancels, that cancels, that cancels. So it's zero. And then I'm sure if you solve for the y direction as well, you'll also get zero. So if the electric field is zero, does that mean the potential is zero? No, not at all. There is a potential at the center, so now we can calculate that. So for A, E is zero, and for B, potential, what is the potential? You got a value for EY? E2, E3, E2 is negative 2Q, E3 is positive 2. Oh, you're right. So this is going to be E2 has a value of negative 2Q, but it's in the up hat direction, so it'll be positive 2Q. E3 is also 2Q. And then yeah, this is E1 and E4. So E1 has Q, and E4 has negative Q. So now you have negative Q will cancel out with one of these, and then you are left over with that. Thank you, Garrett. Almost skipped too far on that one. Let me write this rad 2 over 2 like this. So one of these squared will cancel out with this, right? and then you'll have rad 2 over 2 d squared, and then times 2q. So now we can get a value for that. Okay. Everybody else get 900? I'll have to get my calculator pretty quick. Did they get this for their answer though? Okay, good. Garrett got it as well. Anybody, can you type out the actual? Is it like 900 newtons per coulomb? Is that what it is? $900 newtons per coulomb. And you can, even if you want to, you could say in the J hat direction. 900.14. Let's write that. Okay, there you go. So there's part A. We have, let me fix this. E in the X direction is 0, but E in the Y direction is 900.14 newtons per coulomb in the J hat direction. Okay. So if we have the electric field, how can we find the potential? So we can do that. If you have the electric field already, you simply need to walk the path that you're traveling along to find what that is going to be. And the path is going to be around the square, around the square. Or is the path going to be from the point to the center? What are we looking at? What are we thinking? Does everybody think we should use this? And this will be the potential in general. Just because the EX is 0 doesn't mean the potential will be 0. So from here, you're going to do the voltage is equal to negative. E is what? Q over R squared and the integral of ds. And what's going to be our ds? Also, do I need a substitute for Q? Oh, this is a good question. Which work is required? What's the electric potential at the center of the square? Okay, so there are two ways to do this. You could also the thing I want to point out here is part C of this problem says how much work is required to put the four charges together as indicated in the figure. That is not the same as the potential at the center, but finding that amount of energy could be useful. Mainly because you're going to bring in one from infinity, put it here, and bring another one, it'll do some work. Bring another one, it'll do some work, and bring another, it'll do some work. So this. I wish I had an equation sheet with me. K cubed over r squared. Okay. Yes, you're right. Can you calculate the potential due to each individual charge and then just add them up? Yes. With respect to the center. With respect to the center. So due to V1, which is going to be this, potential at the center will be what? Just KQ over R? KQ over R. And this R is going to be this R that we talked about earlier, which is going to be right. This distance here. The charge is going to be the charge on Q1, and then there you go. So you can do this. Let's just go ahead and go with that approach. So V1 is going to be equal to K Q1 over this R, which is radical 2 over 2 minus D. What about the potential for V2? You're going to have to consider Q1 and this one as well, right? If you want to bring it in with respect to that, then you have to, yeah, you have to consider Q1 as well. So now you're going to want to say AQ2 or radical 2 over 2 times D. This is the amount of potential for the center, and then plus K Q1, because it's due to this Q, over what? This distance D. Okay. Next, V3. Again, you'll have this. And then you'll have, from V3, you'll have this one. And then you'll also have this one, right? So what is this distance now? You have D, and you have D, so then what will that be? Radical 2D. And also, should I be considering my signs anywhere in here? Probably, right? How about V1? V1 is a positive potential. Good. How about V2? Negative potential. Right? Negative. And then Q1 is still positive. Q1 is still positive. V3, positive. So positive. Q2. Remember, Q2 is negative. So this is a negative. Next, last one. V3 due to Q1. Q1 is positive, so plus K Q1 over radical 2D. It's rad 2D is this entire distance. Okay, there you go. And now the last one. V4 will be number 4. Number 4 is negative. Negative K Q4 over radical 2 over 2D. And then due to this one, hold on, let me give myself some more room. Due to this one, plus K3 over V plus, due to this one, Q1 over V, and then finally plus this one. I'm going to want to put a minus there because this is negative potential. Q2 over radical 2 V. So there's a lot of vectors, and you can just, all you're doing here is saying, I have some potential. Why did I calculate V1? Because there's a potential. There is no work done to bring in one charge from infinity, but when you do bring that charge in from infinity, there is a potential. It has potential. It has electric field. So you do want to consider that with respect to the test charge at the center, right? You're talking about like some small test charge at the center. So KQ1, rho 2 over 2D. Then you have this one. This one's negative because that charge is negative. This one's positive because this charge is positive, so on and so forth. Now you have all of these, and all you must do at the end is sum of the voltages is V1 plus V2 plus V3 plus V4. So that'll be the end of that problem. You could also take the sum of here, and this is the answer for B. V net is KQ. Yeah. Yeah, what did you guys get? However, remember for the potential that this is negative and that's positive, but these are more, right? See, the electric field is zero at the center, but is the potential zero at the center? That's my question. Because usually back in the ring problem, you guys remember that even though the electric field, some component of it was zero at the center, there was still a potential at the center. Where am I messing up? Anybody want to tell me where I'm messing up? Because I added all of these. Maybe. Yeah, I got zero by using the same formula as Garrett. Okay. Okay. Yeah. V net at the center. You use the radius r is, or the distance r is this, right? Okay. Okay. Zero. It could be true. Here's a good way to look at it. Oh, just take the v with respect to each charge from the center, right? Yeah, I think you guys are right. I think you guys are right. And to clarify a little bit more, hold on. I'm going to move the computer over this way. Here's a way you can do this. So you draw each of the charges and then draw the electric field from those charges, and that should be able to help you understand if maybe I'm probably wrong here. I think I did work, right? Everybody thinks I think I did work here and not potential. So so what you can do is there's an electric field here. Here. And I have to draw one more. The way you do this is the number of lines that you draw is proportional to the amount of charge. So notice for Q here, I only drew 1, 2, 3, 4 lines. So for 2Q right here, I'm going to draw 8 lines. Four. Seven. Eight. Okay. This one I think I can draw. So this is a very funny picture. Show it to you guys a little better. Here we go. Here's a funny picture. But what I want to tonight is lines coming out. I also have some lines coming out. And I think what you can get from this picture is there's some electric field coming this way, and also some electric field coming this way. And you terminate the negatives, right? Charges always go from high to low potential. And what I think, if I drew this a little bit better, I think you could probably see that there is an equal amount of electric fields going down. Look at, there's this one and there's this one. Just imagine. There's 2 of them coming down right here, and there's also 2 coming up right here. So those 2 coming down and 2 going up will cancel each other, right? And then you also have electric field going this way, and then you have electric field coming this way. So those will also cancel out to some extent. I think you guys are right. All you need to do is say, what's the potential from this charge at the center, due to this charge at the center, due to this one, due to that one, due to this one, right? So I think what I did on the board here was all work. So this would be the correct answer for work, I believe. Okay. Okay. Really quick, I need to plug in my laptop. Make sure I'm right here. I know this is not right for potential, but I believe this is the way you would do if it was energy, right? Energy is, this one is 0, right? And then all I need to do is this. Okay, correct. Right? Because the energy to bring in the first charge is 0. The energy to bring in the second charge is proportional to the first charge. Energy for the third charge is the second one and the first one. And then the energy for the fourth one is the first one, the second one, and the third one, right? I'll rewrite this in a second, but I believe the idea is correct. Okay. I still see 10 people here, so I don't know if anybody posted on the group, the Google group. If anybody could, that would be great. That way, if anybody else wants to see the live stream, they can join on in. Most of you guys are probably from SI, except for, let me see, John. Yeah, did you come to SI, John? I don't know. Shujo, I didn't see you today. Sorry, but that's okay. Let's see. Okay, I've done number 1, 2. We did number 3 in class. or an SI. And I honestly think number 3 is pretty easy. Does anybody want to see any specific problem from this? If not, I'm probably going to skip number 3 and go straight to number 4, or maybe number 6. Number 5 we also did in class. That's okay, buddy. I understand. We try to, like, I have to make sure I don't interfere with 250A and 250B and Chem 111 and all those classes. So totally cool. As long as you guys are getting everything you need to pass this exam. That's all I care about. So anybody want to do a specific problem, please type what problem you want. Number 4, requested by Garrett. Thank you, Garrett. Okay. Okay, so number 4. This is a potential problem and non-uniform. It's non-uniform charge distribution. 4, 6, and 7. Well, 7's a doozy. We'll take a look at 7 later. Oh man. 7 I might have to go do on my own and then shoot up the answer online for you guys. That's a long problem. It's a long one. But it's doable. Very doable. Okay, let's start number 4. You have a thin rod. It's non-uniform. That's the wrong blue marker. Okay. V and okay, so we have a thin rod, and they want to know what's the potential at P. And they want to let us know to take the potential at infinity to be 0. That just means that if you continued along this way to infinity, the voltage would be 0. Okay, B is a constant. And since we have some form of symmetry here, or do we have symmetry? Am I going to use Gauss's law or am I not going to use Gauss's law? That's the first thing I'm going to ask. Should I use Gauss's law or should I not use Gauss's law? I should not. Why? Because there's actually no uniformity here. The only way you would do it is if it was straight down the middle, and then you could probably do something like that. But in this case, we're not going to do Gauss's law. So here you're going to want to take the potential, and the potential for a point charge is written as KQ, with a bad Q, over R. So for a charge distribution, it's going to be V A dq over R integral of that. So now this dq can be done the same way we know how to do the rest of it all. And so let's say dq is lambda dx. Lambda here is this, so bx dx. We already have our variables that we want. B is a constant, x is already in our domain, so we can just go from there. And this is 0. And then this distance here is some L. Right? Let me see. Yeah, the problem gives us L. Dx dx. So you can write that. And what is the r hat distance? Is this r? That's going to be r. This you can call as y if you want. You can call it anything else, but I'll call it y here. So r is going to be y squared plus l squared, right? Yeah, or x squared plus l squared, that works just as fine. And it's actually going to be x. That's actually better. Why? Because we're trying to talk about some portion of the total length. I wouldn't want to use the total length here. I'm actually wrong to put that because then I'm saying it's the total length, and that would be like me picking a point right here, which Brenda says not to do, right? Always listen to Dr. Brenda. Okay. So this is actually going to be x squared. That's going to be x squared. And now you can take this, and if any of these are changing, then it needs to be included in the integral, right? Y is not changing, but x is. So we're going to have to include it in the integral. Okay. Integral dx dx. B is a constant, so I'll take it out. And what kind of integration is this? U sub. I'd like to do a direct substitution. That's weird. YouTube like flagged your responses of U sub. I guess they think you're trying to tell people to subscribe or something. Yes, please subscribe to my channel and also subscribe to PewDiePie because he needs followers. Okay, thank you. Right? Bring that up, integrate it. Or no, am I doing it wrong? Am I doing it wrong? No, right? U to the 1/2. Does Matt not know how to do integration? Yeah. Add 1, 2, divide. Ah, okay. Right. Oh, it is 1/2. That's what I thought. I don't know why I'm tripping. Okay, so 1/2. Oh, right. This is going to be 1/2 as well. The positive 1/2, right, guys? Positive 1/2 on the exponent. Yeah, because that. Okay. Then V is V over 2. And then it's going to be 2 on top. I got 2. Yeah, you're right. Yeah. That's what I thought. I was like, it flips it, right? So there you go. Or is it's already going to be a positive? infinity positive, u to the 1/2, x squared plus y squared, 1/2. That cancels. So then you find the potential is k e x squared plus y squared to the 1/2. Yeah, there's the 2 on top. 2 over 1. kb x squared plus y squared to the 1/2. And what's the next part? So now, also notice here I kind of skipped a little bit. Like what we're assuming here is that v infinity. Yes, somebody asked for the limit. That's what I was wondering. So we're going to be going from infinity to a point p. Oh, yes, it's from 0 to L, but we're talking about potential here. So potential has to have some reference point. It's like we're coming in from an infinity. That's why I drew this here. If you take the x-axis, oh no, I'm sorry. Yes, okay. So imagine this triangle here, and imagine I take P and I stretch it all the way up, all the way to infinity, all the way. Now, if I do that, then this line charge will be like a little small point charge, right? And then as it goes farther and farther away, the potential will be 0, right? Because V at infinity would take reference as 0. So the real way I could have written this would be because I want to come in from infinity. I want to start at infinity and approach P. I want to approach P. So I'm like coming all the way from infinity up top here, and I'm coming down, and I'm hitting P. At infinity, V will be 0. So I kind of did a little bit of skip ahead. Instead of me having to write all that, this is pretty much V at P. V at P. And then our limits of integration will be 0 to L. So then I need to plug those in. Right? L will get plugged in for here. Becomes 0. Right there. L squared plus y squared to the 1/2. And then this 0 will make that. Y squared will be halved. Then minus y. Everybody get that? So there's 2 things I kind of skipped here. The first thing, like I said earlier, you always do have a potential difference. You have to have some reference point. You have to say, okay, I have potential here. I want to measure potential this far away. So we took reference as infinity, said infinity was 0, so therefore I didn't need to say the potential difference is E dot ds, right? That would be a very long, drawn out, way of trying to solve this. Instead, I just said the potential difference is Vp minus V infinity. V infinity is 0, so I can have my reference point of 0, and I can just now calculate the potential at Vp, the normal way, right? Now we have this. This is our answer. And they want to know, determine the vertical component EY of the electric field intensity. If you see this word intensity, it just means magnitude. Don't get scared. And they want you to use part A to solve for this. So part A, part B. What equation am I going to use? This equation. And then for part C, you can use EY is the differential of the potential with respect to dy for part C. So now you just do, don't forget this negative, dy or dx, sorry, dx, kb. This L squared is really like x, right? So let me just write it as x so it makes sense. Okay, take the derivative. Derivative with respect to this, kb and y are all just constants, right? K constant, b constant, y is a constant. So derivative of a constant, 0. And the derivative of all this will be what? Negative kb. And then you're going to have 1/2. You're going to have the chain rule, 2x. And then it'll be divided by. If anybody's not familiar with partial derivatives, all you have to do is hold one constant. Like if you're taking a derivative with respect to y, you hold x constant. If you take a derivative with respect to x, you hold everything else constant. So whatever you're taking the derivative with respect to, that's what you keep. That's what you derive. Yeah, that's what you derive. So here I have kb x squared plus y squared minus y. So derivative of y will just be, I'm looking at this one right here, will just be negative times a negative. There'll be a negative here, right? That's negative. kb, y will go to 1, and then plus kb, and derivative of this, which should be 1/2 2y over this. Okay. I took the derivative of this one, right? Negative y. Oh, I have it right here too. Okay, so for this, I took this derivative. Kb times negative y will be just negative kb. I still have this negative on the outside. And then plus this. Derivative of L squared plus y squared with respect to y will give me, I changed the x here, but it's the same thing. Be 1/2 times 2y, and then over this. So now let me finish that up. Negative and negative, kb. You could probably just pull out the kb as well if you wanted to. 1, that'd be 1. And then distribute this negative. 2 and 2 cancel. You have kby over, and I'll just write it as x squared plus y squared to the 1/2. That makes sense for everybody. So the key part in this problem was be able to find the potential. You have to identify R correctly. And then what is dq? You have to say what dq is. Remember, dq is just lambda dx. And then if we're given lambda, you have to type that in. Right? Oh, you guys can't see that. Use a darker marker. dq lambda dx lambda is bx. Yeah. And then you take this and do your integration. Like that. Okay. So that just about does number 4. Anybody has questions on number 4? That's okay. So for the partial derivative, here's the original equation, and on your sheet you have this. The electric field in the y direction is the derivative of the potential with respect to y. So what you do is, if it's with respect to y, that means everything is a function of y. So you're gonna take anything that has y in it, take the derivative of it. Anything else is a constant. So like here, this can be written as an x. I'm gonna write it as an x. So for here, I'm gonna take this derivative with respect to y. Kb times negative y will just be negative kb, because y is a variable that I'm going to take a derivative of. With this one, all you do is hold the x squared. It's like a constant. This is like saying like 2 squared plus y squared. So you can just hold it and take the derivative of the inside and use chain rule there. So y squared, derivative of that will be 1/2 chain rule 2y. And then because you took the derivative, you minus 1, and the x squared plus y squared ends on the bottom. Pretty much the same thing for dx. For dx, you take everything derivative with respect to x, hold the y constant, and you can do that. All good? Cool. Somebody said they wanted to do 6. Yes? Okay, so this is a 17 question exam. We probably won't get through all of it, but we can try. But the rest of the ones that we don't do, I'll mark off, and I'll make sure I get a solution out there for you guys. Maybe not by tonight, maybe tomorrow morning. I have to sleep as well. I am not a robot. I wish I was a robot. Okay, so number 6. Infinitely long insulating cylinder. It has non-uniform volume charge density. Okay, this one's pretty straightforward. Again, like I always tell you guys, draw your Gaussian surfaces. Okay, there we go. Here, A and B are constants, and this is the radius. This radius. Okay. And they want to just know what's the electric field inside the cylinder and what's the electric field outside the cylinder. Pretty straightforward. What you guys have to remember to do every single time is check your E.dA. How do you do that? What's the electric field due to a cylinder? It's going to be radially outward, right? like this. This is all the electric field. Then I'll take my other marker, and this is your dA. Next, what about here? At the very end of a cap, or even if this was a rod, at the very end, because this is 222, this is, community college physics, we're not going to get into the nitty gritty. Yes, at the sharp corners, there are more electric fields. It can kind of flare out, because especially since it's non-uniform. But here, we're trying to look for very symmetric uses of Gauss's law, right? We're trying to look for supersymmetric uses of Gauss's law. So the electric field at the very end will just look like this. This is not out this way, that's out along the cut end. Here's a candle. If I was looking for the electric field right here, I'm saying that it's like this. It's everywhere around, just like this. Very, very end. So that's what I'm trying to show you guys. Good stuff. Want to smell? Okay. So here's the electric field. And then where's the dA? Just like this. Right? So the angle between E and dA is 90. So even before I do Gauss's law, I'll check my flux. So the flux for the cap is 0, and you can say because E A cosine 90 degrees. Right? Good job. Next, you can do Gauss's law. E dot dA Qn. Now, some of you I see write Qn for a non-uniform problem. That's okay, but you have to remember that you're going to integrate. So my recommendation is always just write it as 1 over epsilon naught integral of dq. That way you're reminding yourself, oh, this is non-uniform, I should integrate, and so on and so forth. From there, E is, where's the contribution? Along the lateral surface area. So this is going to be 2 pi r L. And then I have 1 over epsilon. And what is dq? dq is rho dV, right? Rho dV. What's the volume of the lateral surface area? Anybody know? Volume of the lateral surface area? So the dV will be what am I missing here in my dV? Anybody? Make it clear. 2 pi RL dr. There you guys go. Awesome. dr. Always remember that you're taking the derivative with respect to that, and you're also saying the small volume is changing by the small radius. That's the reasoning. Now I have my dV. I can plug it in here, but I need to plug in rho as well, right? Hopefully I can fit all this here. Let's write it again. Okay, look at that. That's a mouthful. So now you're going to take this whole thing, plug it into your dq. Okay. From this point, you pretty much need to identify what is constant, what is not constant, and pull everything out that you can. You will have two integrals here since you have a minus sign. And what are the limits? Ask Garrett. Well, for A, we're looking at r less than, hold on, let me see what the problem says. I hate problems that have like a little r and a capital R. It's so annoying. But yes, it will be from 0 to little r. Let me relabel this. This is big R. The R of the entire cylinder, right? So right here, we're looking for R less than R. Now just go ahead and multiply this out. You're gonna have rho naught. You can pull rho naught out of here. It's a constant. So I'm gonna go ahead and pull it out. I'm gonna only work with this right side for now, okay? So rho naught over epsilon naught, and then integral from 0 to R, A, distribute the A. Now, since this is a multiplication, you might just want to pull out what you think is constant so that way you're not around too much, right? So let's just do that. Pull out the 2, pull out the pi, pull out the L. All right? Let me just do that. Oh, wrong marker. 2, pi, and L, right? Because I'm going to pull out rho because it's distributed. I'm going to pull out 2 pi, I'm going to pull out L. The only thing I'll distribute is the R. So now, with the integral, I should have something like this. AR minus integral of R squared over B. And then I'm forgetting AR dr and a dr here. Okay, pretty straightforward. This is going to be what? It's going to be AR squared by 2, right guys? And then it will be minus R cubed over 3B, right there. Okay, so now this is that integration part. All this is multiplied by all these constants, and then we'll work with that side. Okay, we're gonna have to do a little erasing here. Is it okay if I erase this integration? I think it's kind of easy. All you gotta do is, distribute it, integrate it, you're done. So erase this integration. And then pull out everything over here. Rho, Q, I, L over epsilon naught. So this is the whole right side of the equation. Okay. Now let's go ahead and work with everything. Okay. Now this 2 will cancel out, this pi will cancel out, this L will cancel out. You always want the L to cancel out, especially when you're talking about an infinitely long cylinder, because that length is infinitely long and you don't know what it is. Just like if you have an infinitely long plane of charge, like a sheet is a plane of charge. Imagine the sheet is infinite. You don't know the area of an infinite sheet. So you always do want to look for those L's canceling out on both sides, or those A's, whatever it is. Okay, so I have 2 pi L cancel, and now I can cancel out this R with one of these R's. right? And then with one of those R's. So then now my final answer should be rho over epsilon naught times A R over 2 minus R squared over 3B. Check that, make sure it's right. Okay. Hopefully that was easy to follow. There's a lot going on. So that's going to be the answer for part A less than R, or R less than capital R. Yes, R less than capital R. Let me just double check. I like to be extra right. Okay. This is like number 75 or something in the book, Gauss's law. Oh, okay, I see. So yeah, this is the right answer. I believe the book has it more simplified. You can pull out, these two have an R in common, so you can pull out that R if you wanted, and then if you pull out this 2, you have to put a 2 up here. So the book answer looks like this, rho R over 2 epsilon naught. If you pull a 2 out from the bottom, it just comes out, right? But if you pull out a 2 and there's no 2 there, you have to put a 2 on top. So that's A minus 2R over 3B. Okay. That's how the book has it, but it's just oversimplification, really. And that's a pretty straightforward problem. Okay, everybody good with this? Maybe thumbs up in the chat or something like that. That way I know we can go to the next part. Gotta erase all this. Okay, I'm gonna assume you guys are all good. I like the 100. That's funny. Oh yeah, and if anybody hasn't heard me already tell them on how to think about when you're in the exam, always flip through all the questions, go through every last one, and identify which problems you are really comfortable with, and then identify which ones you're like kind of and then look at the ones where you're like stay away. you know Try to replace those problems that you're not so comfortable with maybe one of the bonus problems that will definitely help ease your nerves, and then also hopefully you get a better score as well. The other thing I always recommend on doing is drawing huge, like Donald Trump says. But really, take up the whole freaking page, get 2 blue books if you need it, and make sure you're always referring back. You know what's a really easy mistake in this exam? This is a cylinder, right? Here's a really easy mistake. Super easy mistake. That's wrong, right? That is so wrong. If I wrote that for a cylinder, that would just be like crash and burn, right? Because that's saying that's a sphere. So make sure when you're writing Gauss's law, you write that E.dA, you put that Q in. Make sure you're talking about a cylinder if it's a cylinder. Make sure you're talking about a sphere if it's a sphere. Go back to the other, worksheets I've given out to you guys if you need to remind yourselves, like, what's the equation for a hollow cylinder, a hollow sphere, all those things. Okay, let's move on to the next part. I'll write the answer, and then we can move on. oops, could be R greater than R. For part B, it's actually a lot simpler. Reason being is because now you're talking about the total charge, the total volume. So the left-hand side will always be the same. And now I'm talking about this Gaussian surface outside. So it's going to be Qn. What's going to be my Qn? It's just going to be rho v. It's not going to be dq is rho dv anymore because I'm not taking a smaller portion, but you can see it like that. It really depends how you want to look at it. So I'm going to go ahead and write it. Qn is let me just write it as dq. I don't want to confuse you guys. Okay, dq dv rho. And now the v is the total volume, right? It's going to be the total volume. So what is the actual radius? It's capital R, not little r, capital R. Honestly, the only difference between part A and part B is the limits. That's it. So if, yes, the limits. So now I'm just going to be going from, let me see if I remember it. Yeah, I don't want to have to write the whole thing out. It's pretty much the same integration, except you're going to have, yeah, that's how it looks. Okay. Okay. Yeah, I'm looking at the solution. Okay. So pretty much you're just going to integrate from 0 to big R, and then I'm just going to write it out so that way it's not as complicated. So take a look at this equation here. This is for part A. Can you see that? I don't know if that marker is dark enough. Let me just rewrite it. And you know what? I'm going to take this R and redistribute it. So that way it's maybe a little bit easier to see it. There. Okay. So earlier, notice this. This is 2 pi RL. What am I going to change? Is this going to be little r? It's still going to be little r because it's the Gaussian surface. But on this side, it will be from 0 to big R. So it will look like rho over 1 naught times 2. And if you recall, when I did this earlier, I divided this r and it canceled out with one of those. So on the inside here, it'll just be a r squared minus 2r cubed over 3b. And then let me get the left side. I think I'm missing by RL. Yeah. That's what DQ is. Now let me just, E is this 2 pi and the L will cancel out with this 2 pi and L. So there. And then now I have a small r divided by all these big R's, right? Now I can do this. It's going to be rho over epsilon times 2. And then I'm going to have a little r down here. And then times all the big R's. And then what you could do if you wanted to simplify it more, it would just be E is rho over 2 epsilon times r. And then these both have an r, capital R squared in common. So I can pull out that r squared and then just make it a minus 2r over 3b. I'm pretty sure that's the book answer as well. Yeah, rho capital R squared over 2 epsilon r little r, and then a minus 2r over 3b. So that one's not too bad. All you guys got to do is make sure you know Gauss's law pretty well and recognize where the charge is located. That's a fun problem, actually, for me. Okay. Again, I'm gonna have to skip number 7 because I'd really like to get you guys a really awesome answer, and I don't think you guys want to see me sweat on camera. Not really, but it's a long problem, and I'd rather have some thinking time with it. It's a little complicated. No problem, Matt. Garrett. Take care. You can watch the rest later. Anybody want to see number 8? We can do number 8. We did it in the SI today, but I don't. If you guys don't want to, I'll probably skip to number 9. Number 9. There's that. If you're looking for this problem in your book, by the way, it's number 67 in chapter 24 of the 9th edition. Number 67, chapter 24, 9th edition. You can look up that one if you want. Okay. Number 9. Okay, so 9. Oh, these are negative, I see. One, two, three, four, 5. 4, 5. Okay. So this bottom half has charge negative Q. This top half has positive Q. And they want to know the electric field. Awesome. I love electric fields. Okay, due to this segment, like this, due to this segment, it's like this. E, I'm going to put E bottom and E top. So let me try to draw this. There's our, there we go. That looks a little nicer. So then I can draw like a y-axis here. I can call this theta. And then if that's my theta, then I can make this also my theta. It doesn't really matter. You can pick whatever theta you want. You can pick 2 thetas. It really doesn't matter. Okay, so due to this segment, I have E bottom right here. Now, it's a uniformly charged rod, so we will have symmetry. All right, this is going to be E top X. This here will be E bottom X. This here will be E top Y. And this here will be E bottom Y. Okay, so you can see here that due to the diagram, the sum of the electric field in the X direction is 0. And then just sum up the electric field in the Y direction. Okay. So how is this changing is what you should be thinking. It's a rod, so it's distributed along a length. This has charge Q. It's along a length though, so it should be what kind of charge density? Linear, area, or volume? Should all say linear. And that means that lambda is Q over L. What kind of L is this? Is it just a rod or is it an arc length? It's an arc length, right? So this L, you're going to have to find the actual length of L. Like if you had a bent piece of rod, like we get a paper, I bend the paper, and I want to know how long is that actual bent paper. So let's figure that out. If you guys don't remember arc length, it's S is R theta, S is L in this case. So I can just say L is R, right? R times theta. How much is this? Just pi. Yeah, exactly. Yeah, because you have E top going this way, it goes away from the positive charge, and then you have E bottom going towards the negative charge. So you have E in the X direction, negative, and then E in the positive direction. So that's why they cancel. So now you're going to take this L and plug it in. And that directly describes the charge per unit length of this arc. So now you're going to want to just do what you know how to do, right? E is K dq over R squared, right? And what is the R? It's just going to be R, right? R is just the radius. And dq is going to be what? Lambda dx. Am I wrong to say lambda dx, or should I say something else? Lambda ds, maybe. Lambda ds. Because it's distributed along an arc length. So always remember that. Now I'm going to go ahead and put that in, lambda. And let's just say, let's just take a note here on the problem. You're not given lambda. So in the end, this lambda is not allowed in the answer. So that's why I did this whole section here, where I figured out what was lambda. Lambda is Q over R times pi. And I'll plug that in. ds, again, is going to be R d theta. Always, always, always. And in this case, I can just take, I'm going to leave lambda for now, okay? I'm going to leave it. The R d theta over R squared. So you're going to have this R cancel out with one of these. E is then K lambda. And then here, lambda has R inside of it, right? So I should actually plug it in right now to get the correct answer because R is changing, right? Is R changing or is theta changing? That's actually my question to you guys. You can do either or. If you integrate with respect to ds, like this, you go from 0 to 2 pi r. But if you integrate with respect to theta, then you just go from 0 to 2 pi. Pretty simple. So I can actually leave this lambda in my answer for now. So then now it's just going to be 0 to 2 pi of d theta, which is going to be 2 pi, obviously. And then you get E is K lambda times 2 pi over R. Now I need to plug in my lambda, which is right here. K, Q. Notice this pi and this pi will cancel. So I'll be left with a 2. And then I have an r here and an r here, so I have it squared. Yep. And if you guys do dimensional analysis on this, you can check everything's correct, right? That one's pretty easy, actually. Pretty straightforward problem. And that was it for number 9. Wow, that was quick. How did we get 2 pi again? Oh, my God. This is from 0 to pi, right? That's where I messed up. There we go. Good catch. Good catch. Because I'm starting from this theta, right? It matters where you pick theta, because if you pick this theta right here, you would have to go from 0 to pi by 2 and times 2. But if you pick this theta, you can just go from 0 to pi. So that's what I meant. 0 to pi, that pi and this pi cancel. So then you just get kq over r squared. Pretty simple, actually. Pretty legit. Are we given r in the problem? This is a symbolic problem. So as long as you got the answer symbolically, you're good to go. Okay. Anybody want to see another? Yeah, the last equation, it became r squared because we had k lambda over r. And what is lambda? Lambda is q over r times pi. So there was that extra r that got plugged in right there. Yeah, nice. You have to do that because in this problem, you're only given the charge q. You're not given lambda. Otherwise, I could have left lambda in the problem like it was, right? I could have just left it. But here, I needed to make sure that lambda was not in my answer and I substituted everything right. Okay, so anybody have another problem they want to look at? Number 10, if you guys want to do number 10, I'll do for you. However, it is kind of, like you should know it by now, because if you want to know how to do it, it's pretty much the examples in your book. Electric potential due to a ring in your book. Magnitude of electric field at a point P due to a ring in your book. Electric field at the center of the ring, 0. And then potential at the center of the ring has some value. It's the same as the potential at the surface of the ring. So that's all in your book. And it's all from the example problem, so you can probably get that answer. Number 11 is also pretty straightforward, and it is also a problem from your book. So I don't think I want to do that one. Maybe number 12 would be good. Maybe 13. 13 is kind of easy. Let's see. Or whatever you guys want to see. Okay, we can take a look at 12. It has a weird equation. Yes, it does. Everybody, if you give me, I don't know, maybe, 10 minutes? 5-10 minutes? I'm going to take a real quick break, go to the bathroom, grab some tea, and I'll be back. Okay, I'm back. I brought my dog. Say hello. He's a Shih Tzu, and he's very grumpy, and he likes treats. Okay, be gone. My dog. Okay, it's funny looking, I think. He's got a face on him every morning where he like sticks his tongue out, and he just needs 3 treats and he can count them. If only he could do Gauss's law. I don't know. I don't know. Okay, number 12. Look at that. Okay. 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 Cool. 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 I like this. Let's do this. Okay. Okay, cool. So for this one, you're gonna have to draw a lot of vectors, and I think that's the setup. Okay, so due to this charge, how will the electric field be? Pointing that way. Let's call this 1, call this 2, call this 3, call this 4. E1 due to this charge, pointing away. I'm drawing a dotted line here because it's the distance joining the charges. R2. This is also R1. Due to this negative charge, it will go towards it. This is also R3. And then due to this positive charge, it'll also go this way, right? This is E4, and this here is R4. Okay, so now we have that. This is all L. And we're told specifically that the electric field is at the midpoint. This is directly in the middle. So that's the big hint. We're also not given a value of L. This is all symbolic. So let's see how we do this. We're going to want to draw some triangles. It kind of doesn't matter which way I draw my triangles because it's all the same triangle. That triangle is that triangle, right? This is L by 2. This is L. Then what will this be? It'll be L squared plus L squared by 4, which is then L squared 5 by 4, right? And then that will then be, I'll put it as H as the hypotenuse, is the square root of all that. So it'll be radical 5 over 2 times L. Everybody follow with that one? This hypotenuse is radical 5 over 2 times L. And for everything else, and why do I need that? Because I need to know what is the distance from this midpoint to this charge, from this midpoint to that charge. It's going to be rad 5 over 2 times L. And then for these two charges, R4 and R3 is just L by 2. So that's pretty simple. Next, we're going to need to want to use our components. We're going to need to break up our components. Notice for this one, it's going up. E1y. For this one, it's coming down. E2y. E4 is this way. E3 is this way. And then this can be E1x and E2x. Right? So now I have everything. I see that I have E1y coming up, E2y going down, E3, E4, E1x, E2x. Some of the electric fields. What does it want us to prove? So this wants us to do the total electric field, the magnitude of it. So we're going to have to do EY, EX, and the magnitude of all that. Let's do the easy one first. E1y minus E2y. What are they going to have in common? The charge Q. One's positive, one's negative though. And that is shown with these as well. From there, we can do K. The distance from this charge to here and this charge to here is the same, right? We all see that one. We're talking about E2, which is the electric field due to Q2, and E1, which is the electric field to Q1. They both have that big hypotenuse distance, rad 2 over L. So I'm going to factor that out. Right, factor it out. And then what's going to happen? Do you guys see something canceling out here? KQ over R squared, right? I need to square this. E1y has Q in the positive j hat direction. E2y has Q in the negative j hat direction. So is EY 0? Mainly because we have the same magnitude of charge with the same magnitude of charge with the same distance in opposite vector directions. So we're going to have EY 0. I hope everybody got that. So that's actually good because now we don't have to do the magnitude is EY squared plus EX squared is square root of the whole thing. All we now need to figure out is EX, and that will give us the electric field magnitude. So let me erase this. And I'm just going to put EY is 0 because symmetry. Now let's work on EX. I have E3 and E4. Minus E1x and E2x, right? So E3 is going to be due to this charge Q here. E4 due to this charge Q here. And we're just going to have to add them all. What do all these electric fields have in common? They have Coulomb's constant. So I can factor that out, K. But I'm not going to factor out any distances. That's a little too complicated. So let's just factor out K and go from there. E3 and E4. It's going to be Q3 over the distance from Q3 to the point P, which is L by 2, plus Q4, which is 4, over the distance between L by 2. Now I'm going to subtract E1x. E1x, I get to choose a theta, so let's choose a theta now. Choose this. We can choose that as theta. And what will our cosine theta be? Looking at this, it'll be L by 2 over that. So the L's will cancel, right? L by 2 over radical 5 over 2 times L. These L's will cancel. This 2 will flip up, cancel out with this 2. And then you'll have 1 over radical 5, which is radical 5 over 5. So the cosine of theta is radical 5 over 5. I'm going to go ahead and write E1x still has K, so I factored that out correctly. The distance of E1x is this distance, which is rad 5 over 2L. So I'm going to say Q times Q1 divided by, and then multiply by cosine theta, right? Cosine theta. Radical 5 over 5. Okay, we have a little canceling to do here, but we'll do it in a second. The last one, E2x. Pretty much the same thing. Cosine of theta will still be rad 5 over 5. The distance is still rad 5 over 2 times L. So let me just write that again. Q2 radical 5 over 5 radical 5 over 2. So pretty much the same thing because they're the same charge and the same distance away. So now let's do some cancellation. This rad 5 will cancel out with this rad 5, just like that. And then this 2 will go up, right? 2 will go up. So in the end, you'll have K. If I take this L by 2, the 2 will go up. Q, Q3 over L. Is Q3 the same charge as Q4? It is, right? Or the denominator squared? Yes. Yes. Good catch. Good catch. Oh, I can see how this can become messy. Okay, so this is really L squared by 4, right? And then that's what I was trying to get at. These are the same charge, right? Q3 is the same charge as Q4 in magnitude. So you can just add them. Times 2, right? Since they're the same thing, just times 2. Minus now, these two are also the same thing. So I can also do times 2. Yeah, Q1 is the same as Q2, so I can still do that. Q. I can call that Q. And then 2 times let's see. Radical 5 over 2 times this will be, I'll get an L squared, right? Radical 5 will just become a 5, and then square root of 2 will become a 4 on the top, right? And then I'll have Q1. And then this rad 5 over 5 stays the same. Okay, I haven't multiplied by 2 here because these two have the same denominator and the same cosine. So you can just multiply those by 2, right? From here, now you're just going to need to do some math. So from here, I can say, okay, multiply that over, it's going to be 8Q over L squared, right? And then minus, this will be 25, right? And then you'll have an 8 here and times a radical 5. What's the answer? I think we're getting there. We're getting there. At the denominator. So then this multiplies in, right? This is still all distributed. K is still on the outside of everything. So then this will then become 8Q over times radical 5 over 25L squared. Okay. Okay, that looks good. Everybody follow there? I'm going to erase some of this so we have room. And then here comes the last simplifying step to show you the great answer. What do we have in common between these two? I have an 8, a Q, and an L squared. So I can pull all that out, right? So then E at B is A times 8 times Q over L squared. And then I'm taking literally everything out of this, right? 8Q and L squared. So this becomes 1. And then what's left over here? A radical 5 and a 25. And I believe if you check your papers, that is the correct answer. Okay. Yes. Cool. Hopefully that helped. And then they want to know what's the electric potential at the same point. How am I going to find the electric potential? Everybody have a guess? If I have the electric field, how do I find electric potential? Partial derivative, that's a thought. But the thing here, yes, two choices are right, you have to integrate. Why? Because the equation you're thinking of is E is equal to the partial derivative of the potential with respect to space. So that means if you have the potential, you can take the derivative or the partial of the potential to get electric field. I think we did that in the last problem, right? Or the second to last problem. Yes, number 4, this one. Remember, for this one, we found the potential at this point P here. And then we have the potential, we had a function, and then we get the partial derivative to get the electric field. So if you want to get the potential using the electric field, yeah, you can do that too. You can do that too. You could just, if you don't want to mess with any of that, you could just say, okay, assemble this charge with respect to this point, assemble that charge, so on and so forth. You can do that. That's no problem. Maybe you don't want to integrate all this, right? You don't have to. Let's take a look at how to do that. So with this electric field, I can simply say V is integral of negative E dot ds, and I have my E, right? I have my E. And all I have to say is what is changing. Can anybody identify in this equation what is changing? It has to be L. There's literally nothing else that's changing because this is all constants, constant numbers, and so L has to change. L has to change. But then how will you integrate? So this can be a harder way to do it. Sometimes, as Brenda has told you, you can have an electric field, and then let me give you an example so I make sense what I'm saying. Say I found the electric field due to an arc, okay? And then if I want to find the potential at the center of that arc, well, ds is a displacement vector. It's where I'm traveling. If I'm going to travel along this arc length, then that is my ds, right? And then I can model that ds as an arc length, and I can say it's r theta. You know, I can go about it that manner. Or if you have two plates, one's positive, one's negative, and I know the electric field between the plates, then I can travel along that path, ds, this is ds, this is E, and I can say, oh, it's just the distance d. ds integrates to the ds, the d of the plates, right? They'll say something like this. ds from 0 to d because we're starting at one point and going to the other. But sometimes it's actually harder to go about it this way. So integration, if we probably were a little bit more, in tune, not even Calc 4 stuff that's at the university level, then you could do that. But for our purposes, um, we're going to have to just take um, each little potential, each little point, and add them up. That's really just how you're going to have to do it. Sometimes you can try to integrate this. You'll find a lot of problems with it. You're going to wonder where your limits are and where along this whole path are you going to travel. It's really hard to figure that out. So sometimes when you're realizing your ds, your displacement vector, is not really obvious, then you're going to have to just go ahead and assemble the charges and find the potential from each charge. So let's do that. I'll leave that up. This is pretty simple though, I think. You guys should all know how to do this by now. So V is just going to be Q over R. It'll be Q1 and it'll be R1. And then that's V1, right? And then just do all the others. KQ2 over R2. KQ3 over R3. KQ4 over R4. R4 and R3 will be L by 2. R1 and R2 will be that rad 5 over 2 times L that we talked about. Each of these charges are the same value, Q. And then add them up. That's really it. That's really all you're going to have to do there. So that part of the problem is actually pretty straightforward. But the electric field was the harder part. Okay. Anybody good on that part? I don't really want to have to go through all that, but I think that's the basics of it. I think everybody understands. If not, if you want me to show it, I can show it. But if not, I would like to move on to another problem. Maybe 13. 13 would be good. $15 is also a good problem. The signs, what would it add up to 0? Anybody else think it's going to be 0? Just like number 7, I will do that on my own and I will upload an answer for it. Number 14 is a little more involved as well. So I'm going to go ahead and do that on my own and then send you guys out an answer for that. So look out for that. But we can do number 13 or number 15 right now. Shujoy, to answer you, the potential would be negative for V1, positive for V2, negative for V3, and positive for V4, right? So actually it should be 0. It should be. Wait, hold on. I'm trying to think about it. Because what you have to kind of conceptualize is, let's just say there was a function of potential, like v of x, something like that. If I took the derivative of the potential with respect to x, I get the electric field, right? I get the electric field. So we do have a value of the electric field at that point, which kind of tells me that if I took the integral of that, I should have some value. But you're right, because R1 and R2 are the same distance. R3 and R4 are the same distance. Yeah, V should be 0. I'll mark that off in my notes. I'll make sure to get back to you guys on that one. I'm pretty sure though, because your reasoning is correct. They R1 and R2 are the same distance. R3, R4 are the same distance. So you would assume it's 0. Okay. Number 13 or number 15, guys? Please type which one you want to see. 13 or 15? I think 13 is actually kind of easy. Maybe we'll just do 15. 13 is like relatively. Oh, so you can work it out. Yeah. You guys should all know by now that like rubber, glass, and other materials are all insulators, right? So be like glass rod, rubber ball, insulator. Let's take a look at number 15. I love Gauss's law. Okay. Let me just reply to my girlfriend really quick, or she will think I'm ignoring her when really I'm just doing physics. Okay, sorry. When you're with a girl for 4 years, you must reply. You must. No one believes me. They're like, physics, why would you do physics, right? I don't know. Maybe I'm crazy because I like physics. I want to one day build a quantum computer. I've always been interested in quantum. It's really interesting. And programming. So it's like physics and comp sci together. Okay, number 15. Cool. Okay. So I've seen this exact problem on an exam before. Exactly. Or at least, something very similar. Reason why is because she wants to trick you guys. You notice how here you're giving the diameter of the cylinders, not the radius. So don't be too quick on your problems. Make sure you really read them through and really see what's being told to you, because that's really easy for students to lose points there. They'll just say, "Oh, the radius is 3 centimeters." No, it's not. Okay. So make sure you're going slow, not too slow, but slow enough. Um, Radius 1 is 1.5 centimeters. Radius 2 is 4.5 centimeters. And then radius 3 is 6.5. And you do have to convert to, but I'll do that later. But I'll do it now. Why not? Okay, so first question they want to know charge per unit length of the cylinder. You're given the cylinder is made out of non-conducting material, so that's rho. And the outer cylindrical shell is metallic, so it's a conductor. So that means, does it have rho? No, it does not have rho. It only has surface area charge density, sigma. So this has sigma, and this has sigma. Mm-hmm. Okay, so this problem doesn't specify about, they only tell you that the outer cylinder is metallic. They tell you that the inner cylinder is of non-conducting material and has a non-uniform charge density. Rho is C over R. And C is equal to 200 nano, that's times 10 to the negative 9, coulombs per meters squared. So if I were reading this problem, I would take notice that you're given a charge of the inner cylinder, so you know the inner cylinder has a charge. The outer cylinder, all you know is that it's a conductor. And so you should know that if I asked you electric field here, you should say 0. And then the other thing I'm gathering from this problem, yeah, it's interesting. They don't give you a net charge. They don't tell you whether the outer cylinder has no net charge or if it has some net charge. So we're going to have to go forward assuming it has no net charge. So that means this inner surface of the cylinder has negative sigma, and this has positive sigma. If you don't know why the inner is negative and the outer is positive, you should ask why. But if you do know, then you know. Okay, so charge per unit length. They want to know the lambda of the inner cylinder. What is charge per unit length? It's Q over L, right? It's Q over L. And it's infinitely long, but they tell us it's a rho. Oh, he wants to know why. So this has charge per unit volume. And if this has a charge Q, then by rules of induction, if you bring, let me see, this is now a rod. So here's a rod, and this rod is charged. When I bring that rod, say this is a plate. So here's a rod, here's a plate, and I bring the rod close to the plate. The plate is originally neutral. This has charge. The charges on the rod will exert a force on the atoms on the surface area. So it will create a charge separation. Let's just say this has positive charge, right? The picture, it'll help. So say it has negative charge, the rod. And here's a sphere instead. And the sphere has its neutral. These negative charges will produce an electric field, which induce a force on the atoms within the sphere. So negatives repel the other negatives. So all the negatives in the sphere will go to the right side, while all the positive charges will be attracted to the negative charges on the rod. Take care. Have a good night. I'm probably after this problem, we'll probably call the stream, good for the night too. I do have an exam tomorrow for philosophy, but nothing for an E&M SI leader. It's all good. But I want to get some physics done for you guys. Whenever you have charges come next to something that's neutral, it always induces a charge separation. That's why when you take a balloon and you rub it against your head and then you stick it to the wall, it sticks. Not because there's something sticky, it's because you have taken electrons from your hair, they've gone to the balloon, and then you take the balloon and slap it on the wall. And those negative charges on the balloon are much like these negative charges. They induce the charge separation on the wall, or in this case, on the sphere. And so therefore, you have the attraction between the negative and the positive, and the repulsion from the negative and the negative. So that's why in this case, the inner cylinder has a charge Q. Those positive charges want to attract negative charges. So this will have negative charge Q. And then this one is positive Q because we said that the net charge on the cylinder, the outer cylinder, is 0. So if the total net charge is 0, meaning it's neutral, then the amount of charges separated to the inner cylinder must be the same amount of charges separated on the outer, just like this sphere. See how half of them went this way, the other half are here, and they're equal in amounts. There's 1, 2, 3, and 1, 2, 3, and also notice there's 1, 2, 3. So that's why whenever you have something that's charged coming next to a neutral object, it always charges it by induction and induces a charge separation. If you need more explanation on that, I would suggest looking up chapter 22.3 or something like that. It has all the rules of induction. Okay, let's get on with the problem. So lambda is Q over L, and we want to know what this Q is. No problem. We want to know what this Q is. This Q. Now here, let me point something out because this can be confusing. They're asking for the charge per unit length of something that has charge per unit volume, right? Like we're being told that this has a volume charge density, right? Charge distributed over a entire volume. They want to know what's the lambda. How the hell do we find that? Well, I'll show you how to find it. So we're given non-uniform, right? So we know we have to do some sort of integration. We're saying that the charge varies by some function. So if you want the total charge Q, I asked, what is this Q? You're going to integrate dq. So let's do that. Integral of dq is what? dq is going to be rho times v, right? And what v is that? The v of the cylinder. So what's the volume of the cylinder, guys? Maybe somebody can type it in the chat. Volume of the cylinder is going to be pi r squared times L. Everybody got that? Pi r squared times L. And it's going to be, if I'm taking some little charge dq, yeah, that's okay. That's a really easy mistake. I did that a lot too. Make sure when you're doing your problems you like go back and look at whatever you wrote down and you're like, yeah, cylinder, or yeah, sphere, because you can write like E dot dA, do a Gauss' law problem, and you'll accidentally write 2 pi RL when you meant 4 pi r squared, or the other one, you know? It's pretty crazy. So now you got to plug this in. This is going to be rho dV. So what's dV? 2 pi r L dr, right? You need that dr. Now what is rho? Rho is what is given here. So dq is rho times dV. Now identify what's constant here. C is constant, 2 pi, L is constant, R is not constant, but you have R divided by R, so it cancels. So integral of dq is, I'm going to take out the C, the 2, the pi, the L, and I'm going to just have dr. And what are going to be my bounds? From 0 to R. And what are these bounds? 0 to Q. Or if you wanted to get really specific about it, it's going to be 0 to R1, because we're just talking about this. We're just talking about that inner cylinder, right? So R1. So now you find that Q is 2 pi C times L and times R1. You have C, you don't have L. That's the only thing. But what did they ask you for? Lambda, right? Charge per unit length. So watch this. Take this L, divide by it. Q over L is lambda, right? And then you're left with 2 pi C and R1. Wow, mind's blown. So check out how I did that. I started with asking, what is lambda? Lambda is Q over L. I don't know Q, but I know there is some charge Q. Yes, it was wild. Yes, exactly. Sometimes you'll have to use this trick. Integrate dq. Integral of dq from 0 to big Q, just like I did there. And then at the end, you found, oh, I have this extra L. And this is an infinite cylinder too, so you don't actually know the length. It's infinite. So, but then if you take the charge divided by the length, you have lambda. So, wow, great, just great. So take a note of that. There's your answer. Lambda is 2 pi C times R1. C is there. Don't forget your units. R1 is right there, 1.5 centimeters. Here we go. Okay, I'll erase this and then I'll put the answer and then we'll work on part B. Okay. Lambda is A, maybe. Let's label them. I always suggest to label. This is A. This is B. C. D. So I'm inside, right? So I want to say the dA for a cylinder, which is going to be 2 pi A times L. And then it's going to be equal to Qn, which is going to be what? What's going to be my Qn? Now, earlier, when we solved this, it wasn't just for show and tell. It could actually have some use. You can actually just plug in, because you already did you already included the non-uniform charge distribution in this answer, right? So now you can say, oh, well, Q is just lambda times L, right? Q is lambda L. So now go ahead and plug that in. I'm going to take this L and multiply it on this side, right? And it'll be 2 pi C1, or no, C. Oh, I see. I'm going to make this C naught, okay? C naught, C naught, R1 divided by epsilon naught, don't forget epsilon, and then times L. But I don't know L, right? But that's why you want L, because you want to cancel L. Notice there's an L on this side and there's an L on this side. You can cancel those. So now 2 pi will cancel out with 2 pi. L will cancel out with L. And you're going to be left with C sub naught times R over A epsilon naught. Pretty easy. If you don't know how I got there, you should ask. I'm going to move on to part C. Now part C is going to be, this is for R less than R1. This is for R1 less than R less than R2. Okay. Your dA will be the same thing, 2 pi. And this time, according to my diagram, I'm at B. So I'm going to write B times L. And then the right side is going to be the same. Isn't the Q the charge of the whole inner cylinder? Yeah. So for part B, it should be smaller. Yeah, right. I'm going to only integrate from 0 to R1, right? 0 to R1. Let me look at that. Okay. dq is rho, which is going to be C naught over R times dV, which is 2 pi R L dr. Okay, my limits would be from 0 to A. Does that make sense? Because I've labeled A as my inner Gaussian surface here. And I'm not going to do the whole cylinder. I'm only going to do a partial of the cylinder. So from there, cancels. These all are come out. So you have C naught, 2 pi, L, and integral of dr will just be R from 0 to A will be A, right? And then you have 2 pi cancel out with 2 pi, A cancel out with A, L cancel out with L, and then E will be C naught over epsilon. So let me check to see if that's right. What you can do, guys, analysis. So C naught was given as nanocoulombs per meters squared, right? Nanocoulombs per meter squared. Yeah. So then coulomb over, and I believe this checks out because you have meters over meters. You have coulomb divided by coulomb squared, and then you have a Newton on the bottom, so it flips up. Newtons per coulomb. Nice catch, to Joy. You were right. Because really, this R here should have been A cancels out with the A on bottom because we're talking about R less than R1. R1 is the actual cylinder, the actual inner cylinder right here, right here. And a radius less than that is not the total charge. So you're right. This is the right answer for part A. Let me put that. Now I can do that, right? Now I can do what I did initially, because now we're talking about the total charge. Okay, for C, we're looking at R1 less than R less than R2. So that means we're outside this cylinder, but not at this cylinder. We're right here. We're right there. So that means we're going to use the total charge Q, which is what I found earlier. So now I can do that little trick I was just going to do. E, dA of a cylinder, I, and you're always doing the Gaussian surface. Always the Gaussian surface on the left-hand side. So it's not going to be R. I'm not going to write R. I'm going to write whatever I labeled. Take care. Have a good night. So I've labeled this Gaussian surface as B. So I'm going to write it as B. Just know that B is the Gaussian surface. Right here. Okay, and then now I can find what Qn is because I'm going to use the total charge Q of this inner cylinder, right? I'm going to use the total charge Q. So I can just say, I can take this L and multiply it over, and that'll be equal to Q, right? Just take that L, multiply it, that's equal to Q. So then I'm going to copy it, 2 pi C naught times R1 and times L over epsilon C naught. Now let's do some canceling. 2 pi with 2 pi, L with L. You always want that L to cancel on both sides. And then divide by B. C naught R1 over B epsilon naught. And I know it has the same dimensional analysis because we checked it over on this one. C naught over epsilon naught is Newton per Coulomb. And notice I have C naught over epsilon naught and then R1 over B. R1 is meters, B is meters. So still the same thing, Newtons per Coulomb. Part D. Part D, we are right here. And let me remind you guys, because I want a little response in the chat. This is an insulator and this is a conductor. So now we're right here inside the conductor. What should the electric field be? Wait. Electric field inside a conductor. Yeah, 0. Cool. Be confident on the exam when you know it's 0. Don't just be like, I don't know, maybe. No, just if you know it's a conductor and you're inside the conductor, E is 0. And feel good that you're like, yeah, that's all I had to do for that part of the problem. Whatever, Dr. Brenda. Okay, yeah. Got it. Okay, last one. Part E, R greater than 6.5 centimeters. Let's try it. R greater than R3. So now you're going to include the total net charge from the inner cylinder, which is what we got here, right? And the outer cylinder. Now, this problem, like I was discussing earlier, doesn't give too much context. It just tells you that the inner cylinder is an insulator the outer cylinder is a conductor. So you know charges reside on the outside of the conductor, but you're not told if this conductor is charged or not. You're just told that it's there. Does any work have to be shown to prove that it's zero on the test? That's a good question. You should know that electric field inside a conductor is zero by default. And if you wanted like some, wording to kind of add to it, you can say by induction. By induction, charges, yeah, by induction, the charges on a conductor reside on the outside of the conductor. So therefore the electric field is zero. It's pretty much this example right here. Say you have a sphere, it's a hollow sphere, and I give it charge. And the reason why the charge is all on the outside is because if you wanted to find the electric field at the center due to this charge, well, okay, electric field due to this charge would be down, electric field due to this charge would be up, due to this charge would be to the right, due to this charge would be to the left, and so on and so forth. So that's the example that would show you that the electric field is zero inside a conductor. But on the exam, that's just something you're kind of expected to know by now. It's a property of conductors that the electric field is zero. That's why if lightning strikes, you can be inside your car and you won't get electrocuted. So if you wanted to know anything else to write, I would just put this by induction. Right? You can just do it like that. Yeah. Also, charges move inside a conductor, so they'll all push away. That's the other concept behind it. This positive charge is pushing on this positive charge, and that one's pushing on this one, and so on and so forth. So they all want to get away from each other. But no, you can just put E as zero. And other problems, maybe you want to just show your vectors. You can do that too. Show vectors, and then you can prove E is zero in the X direction or whatever it may be. Okay, let's take a look at part E. Okay, how am I going to do this? Okay, let's talk a little bit about some theory about what we're going to think about for this last part. So if we do assume that this outer cylinder has no net charge, then what would be the Q in? It would be zero, right? If it had no charge, then it would not contribute, and so therefore it would just be zero. So you would have the same answer as you had here, right? But let's take a look at a point where that would not be true. Where let's just say we do give this outer cylinder some charge, right? How are we gonna add on that to the answer? So let's do that. I'm gonna change this to say that the Q net is Q. The net charge is Q. So what does that mean for the inner cylinder? The inner surface, I mean, for this surface right here. If this inner cylinder has charge Q, this inner part of the hollow cylinder must be negative Q by induction, right? That has Q, that must have negative Q. If this has negative Q and the net charge is Q, what must the outer cylinder have so that the net charge is positive Q? I'll give you a hint. It's very basic algebra. Yeah. So if the inner cylinder is negative Q, but the net is positive Q, then that means the outer cylinder must have 2Q. Why? Because the charge on the outer cylinder of 2Q minus the negative Q would give you Q, right? So that's the thought process there. And let's just roll with that. So this would be positive 2Q, and the net would still be positive Q. So now let's take a look. The left side is always going to be the same, 2 pi. Right now we're outside and I've marked it as D. I'm going to put D. It's just a distance that I've labeled. That's it. You can put R if you want. And then the QN due to the inner cylinder will be the same. I will write the same exact thing. Same thing. Why? Because I'm outside of it, right? I'm talking about the charge enclosed. Always remember to yourself that a Gaussian surface is a closed surface. So whatever is inside that surface is what contributes to electric field or to flux. So I'm going to add all this, which is going to be 2 pi C naught R1 times L. That is all from the inner cylinder here. But now I'm going to add the charge due to the outer cylinder. Right, 2 pi C naught R1 times L over epsilon naught. That's this one, right? That's due to the inner cylinder plus the charge due to the outer cylinder. We said the net charge was positive Q, right? But we have to put that charge Q in terms of how it is distributed. So what kind of charge is it? Is it a volume? Is it a sigma? Or is it a rho? Oh, I said two things at the same time. Rho, sigma, or lambda. It's a conductor, so it has to be sigma. It has to be sigma. So sigma is Q over A, right? So then the Q would be sigma times A, right? Cool. Sigma here is a uniform charge density. We're not told it's non-uniform. Only the inner one is non-uniform. So you can simply now, this is the Q due to the outer cylinder, and you can plug this in. Q is sigma times A. So then I'm going to write sigma. And then what would be the area, the lateral surface area? That's going to be 2 pi, and this distance here is R3. So you're going to put R3 times L. 2 pi R3, because that's this distance of the outer cylinder. Why not R2? Why would I not write R2 instead of R3? The reason is because where are the charges? Are the charges all on the inner cylinder? No, they're not. Because once they push each other, the net charge is Q, and all the charges reside on the outer surface. Remember that about conductors, charges always reside on the outer surface. So it's going to be 2 pi R3 times L. And I want that L because there's an L here and there's an L here. I don't know the length. It's infinitely long, so I want to cancel that L. If you don't find an L in your answer, there's like literally something wrong. You have to take a couple steps back. And then divide this by epsilon. Let me erase some things so I can put a little bit more on the board. I'll write the answer for C right here. Okay, and now the final step. For part E, I'll put D here. And you can say by induction, or you can even reason symmetry. That's valid. You can say by symmetry, that works too. Okay, so now 2 pi, 2 pi, 2 pi, L, L, L. And now I'm just going to divide by D. So E is C naught R1 over D epsilon naught plus sigma R3 over D epsilon naught. I could combine those, might as well. Okay, well, that was it. I hope you guys got enough from that. I think I've covered almost the majority of problems in this practice exam. Um, for those of you who may have not keyed into my SI, the first practice exam I gave like last week was a little bit easier. Some of them have harder problems, but generally it was easier. But this one, oh God, this one I literally worked with Dr. Brenda. I worked with the previous SI leader and obviously me to, make this practice exam for you guys. It has 17 questions in it. I've tried to answer as many as I can for you guys. And I'll be on campus early tomorrow. So try to get a hold of me if you'd like, or I'll be in your class. I'll be in both classes tomorrow. I'll be there for you guys to help answer questions, help go through things. So if you guys want to work on this during lecture tomorrow, we can. Brenda will certainly allow it. And that's going to be it for tonight's live stream. Thank you all for coming. Please subscribe. Also, subscribe to PewDiePie if you guys don't watch PewDiePie on YouTube. Yeah, should probably subscribe to him. And yeah, good luck, everybody. Get a lot of sleep. And I hope you guys feel ready and not too scared for tomorrow's exam. All right. That will be it for me. I'm going to go get some tea and go relax and call it a night. All right. Bye, everybody.